All right, let's do the thing. Oh, no, I missed it. All right, welcome back, everybody. We're learning about trees today, binary trees. All right, welcome back, everybody. We're learning about trees today. Okay, this sounds fine. Do a quick mic check. I played with this mic a bit, and I don't know. I think it's working all right. It's working better than it was before, but I couldn't even get it to work poorly when I was testing it. So I'm just not sure anymore. All right. I don't think I really have anything I need to talk about with the task, so let's dive right into some slides and do this. Oh, wait, actually, I do have to talk about something. Just scheduling things. So what would be next lecture on Thursday? There is no lecture on Thursday. I'll still have my office hours on Thursday, but there's no lecture this Thursday. In 2 days, there is no lecture. We have Juneteenth. It's a university recognized holiday. Can't have lecture that day. So we do lose one of our 12 lectures, but we'll manage. The schedule's all adjusted to account for that. So no new assignment assigned on Thursday either. So it does give us a nice little break. Summer moves fast, but at least we do get one little breather in there. And then next time we're talking will be next Tuesday, and that will be for the midterm exam. So the way the midterm is going to work is at 8 a.m. Right at 8 a.m. Midterm is the one time where you have to take it during your scheduled section. I'm going to send out an email, and that email is going to have the links for the 4 quizzes. You're going to get 4 links in there, 2 data structures and 2 OOP quizzes, and you'll do them on the tracing tool. You'll click it, you'll get the code. You'll see something like this. You'll have a bunch of code here, and then you'll have to go through the trace of the code. Then there will be a submit button up top that says, and say, go, I'm ready to submit, and it'll say, are you super duper sure you want to look over your work one last time? And you'll be like, yep, I'm sure. And then you'll submit, and then it goes into the grading zone. We'll grade it after that. So that's what's coming up. The midterm is the next thing that happens in this course. So be ready for that. Study for it. Make sure you're doing well on the midterm. And it's nice that we do have this break right here because you can hit the task 5 expected deadline. And then right after that, you're studying for the midterm, prepping for this thing. Crush it. Get at least one of the traces in each category, at least one OOP, at least one data structures, preferably both. And then you don't have to take the final exam if you do well on the midterm. If you don't know what that means, revisit the syllabus or ask in office hours or something. We'll talk about it again. If you don't know what that means. Okay, mic's sounding good. I don't know why it sounded so crappy for so many lectures. I sat down to test it yesterday, and I'm like, I'm going to figure this out. I'm going to do this mic thing, and everything's going to be all worked out with this for once and for all. And I tested it, and it sounded great. So I don't know what changed, but it seems to be working now. It wasn't working before. All right. Trees. Did I click the slides already? Let's download these things and do it. And this is the 7th lecture out of 10, and one of the remaining lectures is a 1-hour files and exception. Oh, I forgot to mention that. After the first hour and a half of lectures, the midterm, and then for the last hour, I'm going to talk about files and exceptions, which you need for task 6. So there will be an hour of lecture next Tuesday, and then there's only 2 more lectures, polymorphism and graphs, and that's it. Then we're at the final exam. So we're already in the home stretch of the semester. That's how quick it moves. All right, trees, full screen. Let's do it. All right, so binary tree, that's what we're talking about today. There can be other types of trees, but in 116, that's all we're talking about is binary trees, meaning they'll have, well, I didn't even introduce what trees are yet. So we saw linked list. Linked list was built off of nodes. It was a node-based data structure, and each node had the value at that portion of the list, at that point of the list, and a reference to the next node. And then we linked these nodes together using using references, using the next reference to be able to. Oh, why is it always something? To be able to get the list structure all together. No, now it's fine. It looked fine in OBS, but then whatever. It's fine now. I'm not worried about it. So that's how we built our linked list structure, is by linking the nodes together through references. Trees are very similar to this. Trees are very similar to the structure of linked lists. Most of it's going to be exactly the same concept that we saw with linked list, except we're going to have references to two other nodes instead of just one. So a linked binary tree, their nodes know the value at that node for that portion of the tree, and two references to other nodes that we call the left child and right child. We can't just say next anymore because there's two next. We'll do next one and next two. We could, but that'd be confusing. So we do left and right. We call these the left child nodes, the right child node, and in relation to the child, its node that refers to it is its parent node. And that's trees. You know trees. Great job, everyone. We did it. So for the rest of the lecture, well, I want to show the code for this. It's very similar to the linked list. But for the rest of the lecture, we want to talk about the implications of this. Okay, so I got references to two nodes. So what? We have to rewrite new algorithms. We'll go through new trace. We'll do some more examples and talk about all the implications of this. But really, this is it. Two references instead of one. That's the difference between binary trees and linked lists. This is what it looks like visually. Where linked list, we had a reference, our variable that we think of as storing a linked list as after a long my eyes can't see this far. Darshan, what up? Yeah, it's been a while. I'm doing all right. And another, I feel like I'm constantly complaining about stuff. Technology just sucks, though. That's why I want to. Yeah. That's why I want to train people to do better computer science and write better software. Because it all sucks so bad. Hey, there we go. Chat wasn't working in OBS. But now we got it. All right, there we go. Now I got chat where I want it. Yeah, what's up? How you been? So this is what a binary tree will look like visually. Instead of where a linked list, we had a reference to just the head node of the linked list, the first node in the linked list. It's the same idea with a tree, except we call it the root node instead of the head node. The root of the tree is the first node that we refer to, and then we go left and right on each node from there to be able to traverse the entire tree. But we only store a reference to a single root node, the first node in the tree. Oops. And I'm going to use this tree in my lecture slides because I think it looks nice. It's nice and symmetrical, and it does foreshadow binary search trees, which we'll talk about later today. This tree is actually a binary search tree, but we'll talk about what that means towards the end of lecture. But this is also a valid tree. So if I have a reference to a node that has a left child, a reference to another binary tree node, but no right child, that's fine. I can also have a node with a right child and no left child, that's fine. And I can have a node with no child nodes, that's fine. Or I can have my nodes with two child nodes, like our tree that we're going to look at a lot. That's also fine. So there's 4 different situations that a tree can have in terms of child nodes. And if there's no child node, we represent that with null, just like we did for linked lists. So this a node can have no child nodes, 2 child nodes, just a left or just a right, 4 different situations. So when you're writing code that handles binary trees, make sure you're checking for all 4 situations. I'll see students get in trouble with things like that. They'll have a tree like this, and they'll say, if left not equal to null, then visit left and right, and then they'll get their null pointer exception when they go to the right. You need to check left and right for null separately. So check, okay, left isn't null, so I'm allowed to go over here without getting a null pointer. But I also have to check, is right null? Okay, right's null, so don't do anything over to the right. Just make sure you don't fall into that trap. I see it all the time, is only checking one of them, and then whatever the answer is, going to both of them, and vice versa. Okay, left is null, so I don't have anything to do with this node, and then you miss the entire right subtree over here. So make sure you're checking them both, even though this is the tree I'll use in lecture for most of the day. Again, just because I think it looks prettier on a slide. That's why I like this tree. And here's the code. There it is. There it all is. And the code for the binary tree actually isn't all that much. Most of this is just me building the tree from the previous slide. A binary tree node, we're going to take a type parameter like we do. We like taking type parameters for our data structures. We're going to have the value at this node, died over here, the value at this node of the tree, and references to the left and right child node of the tree, and then a constructor to set all three instance variables. And that's it. That's all we need. And unlike linked list, the linked list node class, this class is pretty much going to stay like this. Like, this is pretty much all we need. And then our algorithms are going to be written outside of this class. Actually, no, that's not true, because we put the traversals inside this class in the repo, but they don't need to be inside this class. There's no reason for them to be in there. I just haven't moved them yet, but they shouldn't be in there. And then to build a tree, we are going to build trees more manually. We're not going to have a great way to just add nodes to a tree. When we have binary search trees, we are going to write an insert method. We're going to add nodes to a binary search tree with a little algorithm. And we'll get to that. We'll see that. But for the most part, we're going to build our trees manually. Instead of like linked list, we had an append method and we could call append. We're just going to build them manually. So here I'm creating a new root node with the value 5 and references null null, so no child nodes. And then what I'm doing is replacing the child nodes one at a time, saying the left node of this tree is going to be a new node with the value 2 and no child nodes. The right child is going to be a node with the value 8 with no child nodes. And then at that point, after these first 3 lines executed, what we have is we're creating the root node with null null. Then we're saying root dot, let me just double check which one we did first. Root dot left equals a new node with the value 2 and left of right being null. Root dot right equals a new node with the value 8 and left of right being null. And then we're going to one at a time set the child nodes of those nodes. So root dot left equals -3 null null. Oops, going the wrong way. So root dot left equals a new node with -3 and null null. And then for the rest of the 3, Huffman's algorithm to optimize tree and its prefix code. And the other 3, we're just rounding it out and building the rest of the tree. And this is how it's going to look in your trace for the midterm coming up. Is we're going to build the tree manually like this. I can guarantee at least one of your traces, one of your data structures traces, you're going to see code that looks similar to this. And it doesn't look like it on the slide, but this code is in the main method of the binary tree node class in the repo. So that's why I'm allowed to do root.left, root.right. Even though those are private instance variables, this code is in the repo inside a main method inside the binary tree node class. So I am allowed to access those instance variables, those private instance variables directly. So we'll see something like this. I'll even go a step further and say there will be 4 nodes in that binary tree with on the trace. With 3 nodes or less, I just can't do enough with binary trees to assess if you understand binary trees properly. With 4, I can, and anything more than 4 is just tedious. It's just making you go through extra work for no extra benefit. 4 is the exact number that I need to know that you understand how a binary tree works, specifically the traversals that we're about to talk about. Okay, speaking of traversals, let's talk about them. So we have references to 2 nodes. How do we even traverse a tree? I just want to do simple stuff. I just want to visit every node in the tree. That's it. It's a simple ask. I just want to visit every single node in the tree. Maybe I just want to print everything out. Print every node that I visit, print out its value, which is usually what I like to do with the example because it's like the simplest thing we can do, is just visit every node and print them all to the screen. So how do we do it? Well, it's actually ridiculously simple. Really simple to do this. In concept, of course, the first time. Is with linked lists, and this is where we finally get the payoff of all that recursion we did with linked lists, and hopefully some of you at least took my advice of using recursion on your task 3 with linked lists and getting practice with recursion, because now when we make the recursive call, like we would make a recursive call with the next node with a linked list, well, with trees, we got 2 nodes, references to 2 nodes, we make 2 recursive calls. That's it. We're done. Recursion and the stack do all of the work for us. We just make 2 recursive calls, and that's it. It's easy as that. Very, very, very easy if we're embracing our love for recursion. Now, those of you who did not take the advice and wrote all of your linked list stuff with loops and don't understand recursion yet, that's going to be a lot trickier to do these recursive calls. If it's the first time you're ever writing a recursive method, it's a bit trickier. And we're going to look at 3 different ways to do this, and they're all pretty much the same exact thing. Pre-order traversal, in-order traversal, and post-order traversal. The only difference is the order in which we'll visit the nodes. The code for all 3 will look almost identical. So let's take a look at in-order. I'll explain in-order traversal a bit in depth. Then the other 2 traversals, I'll just say, yeah, they're pretty much the same thing. So in-order traversal, what we're going to do is check, and this code is written a little different than the way we saw the linked list recursions, in the sense that I am sometimes calling this method. Actually, I think I did this with the min of a linked list of doubles. Is I'm always making the recursive calls. There are 2 choices here when you're doing recursive calls like this. You can either check if left is null, and if left's null, don't make the recursive call. Only make the recursive call if left is not null, and same with right. Check, is right null? If it's not null, make the recursive call. I'm not doing that. I'm always making the recursive call unconditionally, and then sometimes my method is being called where node is null, the current node that I'm visiting is null. So when it's null, I want to make sure that I'm not using the dot operator on it, because then I'll get in trouble. All this dot value, dot left, dot right, all those would be null pointer exceptions if node is null. So if node is not null, I'll do that stuff. But if node is null, I'm just doing nothing, returning empty string here. If node is not null, so when I first call this, it'll be on the root node of the tree. And if node is not null, what I'm going to do is initialize a string and then make the recursive call to the left and accumulate that into my variable. Then handle the node itself. Whatever I have to do here, I'm just concatenating all these to a string, basically a 2-string method. I'm going to concatenate the value at this node to a string. I'm allowed to call toString even though I don't know its type, because every object in Java has a 2-string method, like we talked about last time. Accumulate that, and then make the right recursive call, and whatever it returns, accumulate that. So what we should get is the entire left subtree as a string, meaning the left child node and all of its children, children's children, etc., all that converted into 1 string. Then I'm going to add in this node's value and then the right subtree as a string, and then return that. And if recursion's doing what I want it to do, with the base case of the recursion being the node is null and just return empty string on null, this should give me what I want. It should convert the entire tree, all the values in the tree, to one single string, space separated all the values, and return that string. It looks pretty much like it toString did with linked lists, except we have two recursive calls. So if you've embraced recursion, this code should be pretty trivial to look at. If you have not embraced recursion yet, good luck on task 5. It's just gonna it catches up to you. It's like you gotta learn recursion eventually if you're gonna be in computer science, and maybe you'll even stumble your way through task 5. But someday you're gonna have to learn recursion. Embrace it. It's fun. Recursion's great. Recursion is one of those topics that's really hard to understand, but once you do understand it, you really do start to embrace it. Anyone who I know who has gotten past that hurdle and finally it clicks, oh man, recursion makes sense now, then they want to use it everywhere. Okay, and then pre-order traversal. The difference between the traversals is when you process the node's value in relation to the recursive calls. So in order, we process the node in between the two recursive calls. Pre-order, we're going to process the node and then make the two recursive calls. And post-order, we're going to make the two recursive calls and then visit the node. So all we're doing is changing the order in which we process the information. That's the only difference between the three traversals. The concept of making two recursive calls and also processing the node, that's all the same, but it's just the order in which we process them. Only difference between the traversals. And that's it. That's all the code for all three traversals. In order, process the node in between recursive calls, pre, before, post, after. And that's how we visit every node in a binary tree. It's just one extra line over how we would do this with a linked list. We added a little extra stuff here, initializing a string on its own line, having two different return statements. We could condense the code a little bit, but and we will. When we get to the trace, I'll be printing to the screen instead of accumulating into a string, and it will be a little less code. But not much extra code, just one extra recursive call from linked list. Now here's my challenge to you is take one of these traversals, whatever your favorite one is or whatever, and try to write it without recursion. With linked list, this was an easy ask. You could write it as a loop, and many of you do. Write your linked list algorithms as a loop, and it's not that big of a deal. You just do while node not equal to null, process the node, and then node equals node.get next. It's not that big of a deal. Try to do that with trees though, because this is where recursion really pays off, is with trees. Try to write any one of these without recursion. It is difficult. It's possible. Over the years, I've had, I think 3 students did take me up on this, and they showed me their code. I always like seeing the code. If you do take me up on this, I'd love to see the code. Come to office hours or email to me or anything. I always like when students take me up on this. But it is always way more complicated than these traversals. It's usually, I think the cleanest solution I saw was, I want to say 20 lines of code. Because you have to keep track of a lot of information that the recursion and the stack is keeping track of for you. When you have recursion like this, it's the stack and the order of the stack frames, and we'll see this when we get to the memory diagram. The order of the stack frames is keeping track of a lot of information for you, and if you don't use recursion, you have to maintain all of that information. You have to remember that. You have to have some data structure. And if you are going to take me up on this challenge, I recommend using a stack. Since you're using the memory stack to keep track of a lot of information, you kind of want to simulate that same information storage with an actual stack data structure. And you got to keep track of how many times you visited each node, because each time you get back to a node, are you about to go to the left child? Are you about to go to the right child? Are you done with the node? You got to keep track of that information of how many times you visited that node, because you need to know where to go next. So it's quite a bit of extra stuff. Quite a bit of extra stuff to keep track of. All right, and I'll go through these really quickly, just what order the nodes are visited in a tree. I'll just talk through these on my slides, but we will get to a trace where I'll slow it way down and go through every single step for an example. But quickly, just to show the difference between in order, pre-order, post-order, this is an in order traversal. The way we're going to visit the nodes, we're starting at the root, because we're calling in order traversal on the root node. So we're starting here, and then the first thing we do is go to the left. We're going to make a left recursive call. And that node, we make a left recursive call. Then we make a left recursive call. That recursive call gets an input of node equal to null. So we do nothing. We return empty string. Then we get to this node, which just made its left recursive call. So now we're going to visit the node and print 3 or accumulate 3 into our string, -3 to our string, and then make its right recursive call. That does nothing, returns, and then this is the third time we're visiting this node. We just got back from the right recursive call, and then we're going to return -3 as a string back to this node, which just made its left recursive call, so it's going to process its node, so 2 is next. Then its right recursive call, left recursive call, 4 is next. Then its right recursive call, return, visit 5. Then make it right recursive call, left recursive call, return, visit 7. Right recursive call, return, print, get 8. Right recursive call, left recursive call, return, 14. Right recursive call, return. So we get the entire left subtree. So we got -3, 2, and 4. Then the root node, process the root node. Then the entire right subtree, 7, 8, and 14. And that's true for every single node. When we got to 2, we went to the left, then visited this node, then went to the right. So that's the order we'll get with an in-order traversal. With a pre-order traversal, we're visiting the node, then making the recursive call. So the root node is always going to be the very first thing in a pre-order traversal. So we get visit 5, left recursive call, visit 2, left recursive call, visit -3, left recursive call, that's null, so it just returns. Right recursive call, returns, return. Right recursive call, visit 4, recursive calls that do nothing, return, over to the right subtree, visit 8, then 7, then 14, and then it's all returns after that. So we're visiting the node, the root will always be first, and then go to the subtrees. Post order, we're going to make our recursive calls first, so the root is always going to be last. We're going to make a recursive call, visit -3 first, return, call on the right subtree, the right child. 2 recursive calls that do nothing, and then visit 4 next. Return, visit 2, return, right recursive call, left recursive call, 2 recursive calls, then visit 7, then return, right recursive call, visit 14, visit 8, visit 5, and then return. So we did both recursive calls before visiting the node in question, the node for that stack frame. So a lot of different behavior just based on the order in which we make these calls. Yeah, finish this tea. So different orders, and I see that. Why does it do that? That right there. Why does the green screen just pop up randomly like that? Then it goes back to just perfect. It's because technology sucks. And I say that kind of lightheartedly, but I really do feel like technology's already peaked. It's just getting worse every day now. It peaked like 10 years ago. I think we had the best form of everything. It's kind of sad that things just seem to be getting worse. In some regards, they're getting better, but just common day-to-day things I feel like are getting worse. Some things, don't get me wrong, are getting a lot better. Where's my binary tree node? I'm in the wrong week. Binary tree node. I'm just going to grab all of this. And I'm only going to have, is this true? I'm only going to have one trace. This is the only trace that I'm going to have with trees. I mentioned this before, but the only new thing that we're seeing in this trace is the fact that we have 2 recursive calls. But there's nothing new with tracing. Like, there's no new tracing content with that. You map a recursive call just like any other method call, but I do feel obligated that I should show you at least one example of making 2 recursive calls. So we will do exactly that. I remember we have this. I'm not going to do something like this on the quiz. I forget why we have that. In order traversal, post order traversal, like why? Oh, because it's static. That's why. And we're in the class of the binary tree node, and that's what I'll do for the quizzes too. So we can just do dot left, dot right. Otherwise, like this line right here would be root.getRight.setLeft of new binary tree node. You'll have to do that for your programming assignment for the programming tasks, but that's fine. We can call getters and setters. But when you have to do that in a trace, and that's 2 extra stack frames for this line, it gets a little tedious. Just building the tree is so many stack frames, and I don't want to mess with that. You don't want to mess with that either. I don't need any of these getters and setters. Let's get rid of all those. And right here, we're looking good. Hide toolbar. Like this mic, for example. You used to be able to just plug in a mic and it just worked. I don't know. Maybe I'm just buying crappier stuff. I don't know. So we start with the main method. We put root on the stack, or in the main stack frame, and then new binary tree node. This. I think companies, if I'm going to give that a more serious take, I think companies are just trying to stuff way too many features and just extra stuff that no one ever needs. 10 years ago, and especially even longer ago, everything was a lot simpler. It's like if I bought a mic, I want it to act as a mic, and that's it. But now everything's got to have AI in it, even though it doesn't need it. How come when I start a Zoom call, it's always screaming at me, hey, we have an AI assistant now? I don't need AI in my Zoom call, man. Like, I don't need that. All right, value. I feel like I get to rant during constructor calls because we've seen this so many times. OX100 day null. So when we hit our constructor, we're just assigning the instance variables, so these get day, null, and null. And this returns OX100 over here. So we effectively have a binary tree with just one node. We just have the root node with the value day and no child nodes. And then the next line, we're going to replace this null with a new binary tree node. So we're going to get another binary tree node constructor. This, we see the keyword new, so we're creating a new object on the heap. Match the type, map the constructor. We're going to have value, and even with 4, value left and right, even with 4, you're going to see this gets a little tedious. We got to create 4 nodes in the tree. That's just the way it's got to be. I need 4 nodes to be able to write an effective binary tree node tracing quiz. So there will be 4 nodes on the quiz, and I'm going to have to live with that in lecture. You're going to have to live with that on the quiz. It's just going to be a fact of life. We got to go through this little bit of tedium. Even though once you do one of these constructors, I know you can do the rest, but we got to do it. Have, oh, type, null, null, have, null, null. And even though this is being returned and then stored into a variable, we don't have any way to return to a variable that's on the heap. So we're going to forget the return arrow. We're just going to cross this out and know that it got sent to root.left. So root.left equals whatever this returned, which that resolves to a reference to the object that was created. So left, oh no, oh no, oh no. That's not how we do it. Null, cross out null. Null is replaced with, so the value of this variable was null, and we updated its value to OX200. And then next line, do it again. Another binary tree node. We see the keyword new, so I know I'm creating a new object on the heap. It's going to have value left and right. Let's run it back. Value left, right, this. OX300, value left, right, great, null, null, great. Oh, I have a feature request for this. I want tab to be able to send me to the next box, so I'm not using my mouse so much. This returns into root.right, so root.right equals OX300, and then one more time, new binary tree node, map the constructor. This, we got OX400. We're going to have value left, right, value left, right. So a little bit of tedium here, but not too much. Admittedly, this isn't taking too long, but it does take a minute. I wouldn't give you a tree with 8 nodes on a tracing quiz, because once you do this a few times, you get the idea. But I do need 4 nodes when we do a traversal, or else you could, like with 3 nodes, if I have a, no, that's not even true. It's not quite true. But I need 4 nodes to really show, really have you show me if you understand the recursive calls. I'm always going to say with 3 nodes, a root and 2 child nodes, in order, pre-order, post-order do the same thing, but they don't. They do the same recursive calls in the same order, but they do visit the nodes in different order. So technically we could get away with 3, but I feel like with 3, I don't know. I don't want to rethink about it right now, but I thought about it before, and we need 4. I forget the exact reasoning why. There's something where the traversals kind of blended together. But with 4 nodes, the traversals don't blend together so much. So root dot right dot left, and replace this with that OX400 that we just created. Okay, so the start of your binary tree trace is going to look like this, a whole bunch of constructors and getting a whole bunch of objects on the heap. So right now we have root referring to the node OX100 with the value day. Its left child is 200 with have and null null. And then its right is 300 with a value of great, a left of OX400 with the value A, and then a right of null. And there's one case where I do want to jump back to the slides because I have a visual once we create all those, just to visualize what the tree is. It's this tree. So our root is day with a reference to have, a left of have, a right of great, which has a left of A. And I do recommend this on your traces. Have some scrap paper sitting there and sketch out the actual tree that you have, because it can help you visualize it. It's a little hard to look at the heap and all the references, follow all the references, and figure out what tree this is. But if you sketch it out here, it's a lot more clear what you're working with, what the data is, what the data structure is. Okay, let's traverse this thing. So let's do traversal. This thing I'm not gonna do on a trace, so I don't know. Don't worry about it. But for those of you who are wondering what this syntax means, this is a method that takes a type parameter. Now, most of our methods that use type parameters get their type parameter from the class itself, so they can just use that type parameter all over the place. Since this method is static, it doesn't belong to an object of this type, and the type parameter is only set when you create an object. So since this is static and belongs to the class, it doesn't actually get this. It can get the variable, but that variable is not set to anything. So we have to say this method itself takes a type parameter, and then we can use this type parameter. So we do need this on our static methods, but I just won't give you a static method on the trace. Or actually, I take that back. I will give you a static method on the trace, or else the traversal stack frames, you have to put this in every single one of them. That gets a little tedious too. I'll give you a static method, but I'll hard code. I'll give you a special binary tree node class that has a hard coded type in it. So we're not going to use type parameters on the trace to get around that. Or else this is just, if you know what it is, you know, but if you don't, it's confusing. And it has nothing to do with your understanding of binary trees and their traversals. So I don't want to do it. All right, so we have a call of traversal. We're not calling this through any object, which it's been a while since we've seen a method like this. So we're not calling this through any object. We're just calling it directly because it's a static method, meaning when we put traversal on the stack, this is our first method call in a long time that does not have the keyword this. So we don't have this in the stack because it's a static method. It's called through the class, not through an object. So there is no calling object to put into the keyword this to have a reference to. We have node. We are keeping track of which node we're currently visiting through the parameter. And node is initially root, which is OX100. Okay, let's call traversal. If node is not equal to null, node is not null, looks good, then make these, do this stuff. So the first thing we do is a traversal call. So we're going to put another traversal, let's say, clipboard to that. We have another traversal stack frame where node is node.left. So node.left 200. Okay, let's scroll this up, down, right there. OX200 on this recursive call. And we're going to have a lot of recursive calls on the stack here, so get ready for a lot of recursion here. With this traversal, node is not null, so we're going to run the code. And as we're running the code, as we're going through this traversal, it's important to remember what each stack frame is doing. This was always true, but it was always trivial in the past. Now, whenever we get back to a previous stack frame, there are two different places where it can be. It can be It could have been waiting for its left recursive call to resolve or its right recursive call to resolve. So we have to remember which one each recursive call was waiting for. So this one, OX200, it's not null, so we're going to make its left recursive call. And this is a combination of a lot of things I keep saying is, one, just do what the code is telling you to do, and you're not going to make mistakes. Just go line by line when you're doing these traces next Tuesday. Go line by line and just do what the code tells you to do. I'm making a call to traversal on node.left. Node.left is null. So node, the parameter, gets the value of the argument null. And this stack frame is going to run the method. If node not equal to null, that's false. So I don't do anything, and this just immediately returns. It returns back to this stack frame here, which just made its left recursive call, which is something, again, you just have to remember or mark it down on your I guess you can't really on the tracing tool, but on a sheet of paper, mark it down on a sheet of paper as you're going through your trace to remember where each stack frame is. This one is waiting for its left recursive call. Since it just got control back again, now it's going to move on to the next line, its right recursive call. It's going to make a traversal call where node is node.right. So node.right is null. So null. If it's null, this stack frame just doesn't do anything, skips all the actual code, and returns again right back to this stack frame here. But this time, the stack frame just made its right recursive call. So now it's going to move on to the next line, and finally we're printing something to the screen. We're going to print this node's value. Node.value is have. So we're going to print have space to the screen. And notice I'm using print, not print line. Again, this is something I would never, you would never fail a quiz for missing, oh, that was print, not print line, gotcha. That's not ever going to happen. But I want the formatting to look proper in lecture. So I'll use print instead of print line here because I want all these printed on the same line. Okay, so this node printed to the screen, got to the end of the if statement, so it's going to return back to this original recursive call. And this one was waiting for its left recursive call to resolve, so it's going to move on to its right recursive call. So node, make a traversal call to node.right, which is 300. So node is OX300. This stack frame starts the method over again. Every recursive call, just don't even think of them as recursive calls. It's just a method call. You call the traversal method. You run the code for the traversal method. So node is not null, so we're going to run the code. We're going to make the left recursive call. So we're going to put another stack frame on the stack where node is node.left. Node.left, OX400. And then we start over again. This stack frame now has control. We just pushed onto the stack a new stack frame. This stack frame is going to run. Node is not null. So we're going to make its left recursive call. So we have traversal where node is node.left, which is null. Since node is null, we're not going to do anything. Get right back to this stack frame, which just made this recursive call. Now it's making the next recursive call with node.right, which is also null. And right here is where I want to park for a minute and just take in what's happening with this code, with this program. A few things. One, we have 1, 2, 3, 4 stack frames on the stack right now. And the important thing with this one, I'll keep saying it, is remembering where each stack frame is in its call. This stack frame, the active stack frame, well, it doesn't really matter where it is because it's about to do absolutely nothing. It's going to check the conditional and return. It's going to return back to this stack frame which just made its right recursive call. So when this stack frame gets control again, it's going to print itself to the screen and return. It's going to return back to this stack frame. When it gets back to this stack frame, it was making its left recursive call. So when it gets control again, it's going to go to the right and make its right recursive call, and then do what it does to the right, which is going to be just null, and that's going to return back to the stack frame again, and then it's going to print to the screen and return, all the way back to the original method call, which is making its right recursive call. So once that resolves, it'll print itself to the screen and return. And that's where the sketch paper, if you draw out your tree and kind of draw out where you are in the traversal for each node, you can keep track of all that and not lose track of what you're doing when you get back to a stack frame. So this right here, this is as complicated as a tree traversal is going to get, where we have 4 stack frames all in different spots in the code. So if you understand this snapshot right here, what's happening right here in the program, you're going to do just fine on your data structures quizzes next week. If you don't understand everything that's going on right here, that's fine. A lot of this is brand new. Summer goes super fast, but you got some studying to do before next Tuesday. The other thing I want to mention here is the way we're making the recursive calls. What I'm doing here is always making the recursive call, like I mentioned before, and sometimes I'm calling this method where node equals null. I'm putting the frames on the stack, and then those frames just don't do anything. The other option is to check, I would say something like if node.left not equal to null, then make the recursive call. If node.right not equal to null, then make the recursive call. So I could change this from 1 null check to 2 null checks and conditionally make the recursive calls. So if I do that, then I would not have these extra stack frames because I'm never calling them with null. And I like to switch that up from the lecture example to the quiz to make sure you're actually reading the code, because something I see a tremendous amount of, a kind of upsetting amount of, is students overstudying, as weird as that one sounds, overstudying and overthinking these traces. I say the overthinking a lot. But the overstudying thing is they'll look at the lecture example and see all of these nulls, all these stack frames with null, and then think, when you get to your quiz, think, oh, well, I need a whole bunch of stack frames with null because that's how Jesse did it in lecture. Don't fall into that trap. Do what the code tells you. What I need to know on a quiz is, can you trace code and know what's happening in memory? At no point in CSE116 or your whole CS career, at no point am I going to be interested in, can you memorize a lecture example and regurgitate it back on a quiz? That's not what we do in computer science. We're trying to arm you with tools to be able to solve novel problems. There's very little memorization involved in really the whole degree. Maybe that's a little exaggerated. There are some courses where there's just stuff you got to know. But when it comes to the programming aspect of computer science, at least, very little memorization. We're arming you with tools, and can you use those tools to solve problems you've never seen before and that we've never shown you before. So I like to switch it up. So just don't be on guard for that. Just do what the code tells you to do. Here, when I trace through the code, I got a call like this: traversal, node.left. Node.left happened to be null, so I make a recursive call where node is null. If you see the other version of that in the quiz, if it says if node.left not equal to null, then make the recursive call, that code isn't telling you to make a recursive call where node is null. So don't make that recursive call with node is null. Just do what the code is telling you to do. Trace through the code that you're given on the quiz. Don't regurgitate the lecture example back to me. Not asking you to memorize. I'm asking you to be able to read code. Because that's what the quizzes are all about. The traces are all about, can you read this code and understand what it actually does? Which I shouldn't have to convince you is a very important skill. Being able to read code is an extremely important skill. if you're expected to be able to write code. Like you have to, I'd argue that you have to be able to read code before you can write code. So if you can't read code, you got some studying to do. You got some work to do, which is fine. I mean, learning takes time. So let's get back to this trace. This stack frame does nothing, returns control back to this stack frame. We have to remember what it was doing. It was making its right recursive call. So now it's going to print itself to the screen. Node dot value is A. So we're going to update our line. It's still on the same line because we did print instead of print line. And then it returns. That's the last thing it did. Control back to this stack frame, which just made its left recursive call. So this just resolved, so it moves on to the right recursive call. So we have traversal node dot right is null. So node is null, which just does nothing and returns back to this stack frame. Now it's going to print to the screen. It's going to print its value. Node dot value is great. Space. And then this stack frame returns back to this one. Remember, the crossed out ones are not in memory anymore. So the stack right now is this traversal call and the main method. Those are the only two stack frames on the stack right now. And the top of the stack is the traversal call. This just made its right recursive call, so it's ready to print to the screen. Node.value is day. And our sentence makes sense, so it's a good indicator that we traversed it right. It won't always be true on the quizzes, because then, like, if this were the quiz, students will be like, oh yeah, I can see what the sentence is. Then you just write that and mess up your traversals. So print that to the screen. It returns, goes all the way back to the main stack frame. It was making this traversal call. So that's the end of the program. Main stack frame's over. Which means... No, actually I will. Never mind. I was going to say, which means that's the last memory diagram I'm doing over the summer. But I will do one more. With polymorphism, it doesn't show up on any quizzes, but there's still some things I want to talk about that I just think are shown better through a memory diagram. So I guess I will do polymorphism trace. So that's our tree trace. So if you have questions about tree tracing, or any tracing before the midterm, hit me with it. If not, we're moving on to BSTs. Oh yeah, we got some... We have some example time in this lecture. Yeah, we move right on to BSTs. This is one case where I will get some live coding in the 8 a.m. lecture. Yeah, sorry, I just had to refresh my memory quick. So let's go back to the slides. Close this. Close my mic checked tabs. Let's go right into BSTs. Binary search trees. So we just saw binary trees, and we want to see at least one application of them, because throughout all binary trees, at no point did I ever say why we would ever use one. Why would we use a binary tree? And it actually take a while to get to and answer that question when we get to the end of our binary tree talk. But let's talk about binary trees. Let's introduce these things and then talk about why we would ever do something like this. But let's talk about binary. I do mic checks every once in a while to make sure. All right. So a binary tree, or a binary search tree, a BST. The definition of a BST is that for every single node in the tree, everything in its left subtree comes before that node's value in fully sorted order, and everything in the right subtree comes after that node's value in fully sorted order. And the only edge case is duplicate values. How do we handle duplicate values? Well, it's up to specific implementations. We can handle them any way we want and still call ourselves a BST. But these first 2 bullet points, these are the important ones. And every comparison to decide, does the left subtree, does it come before or after? All comparisons will be made using a comparator. So we use a comparator to have a BST that sorts in any order. Now for the lecture example, I'm going to use the less than comparator with ints and just get ints in increasing order, just default int sorting. So in lecture, I will start saying everything to the left is less than, everything to the right is greater than, and then ties. I'll break ties to the right once we get to the code, but we're not going to have any ties anyway. But the code has to answer that question of how to handle ties. So the comparator is an int increasing comparator, which is the less than operator. So I'll say less than and greater than in lecture, just because I'll get sick of saying less than comes before according to the comparator and comes after according to the comparator. It's just a mouthful. Less than, greater than, just rolls off the tongue a lot easier. But it is all comparator-based comparisons to determine the full order of a BST. And for your task 5, it's going to be a BST of songs that are sorted based on the comparators that you're writing in task 4. So either a song title comparator or the Bayesian average comparator. It's going to sort in a different way based on whatever comparator you give it. So will all be comparator based, but for lecture the comparator is the less than operator. So for BST, here's the start of it. We will expand on the BST code. It's not like the binary tree node code where just there wasn't much that we had to add to it. BST, we will add 2 specific methods to this thing. So first, the BST is going to have as an instance variable the root node of a tree. This is just like the linked list of doubles, just like the song class having a linked list of ratings, a reference to the head of a linked list of ratings. Same thing, a BST is going to have a reference to the root node of its underlying binary tree to be able to store a tree that will have the properties of a BST. And I'll say this now before I forget, but the BST, just like any other code, since the BST is in the examples repo, you can grab the BST code and put it right into your project if you'd like. Some students like to recreate a BST, that's fine too. And just take the BST methods and put them in their code. If you want to do that, that's fine. Or you can just take the whole BST class and in your code say new BST of whatever comparator you're given, and then use that to store your BST. But you can use all the BST code that we're going to see right here, and that's what you're expected to use to get your test 5 stuff done. Okay, so BST is going to have the root of a tree, which is initially null, because we haven't added anything to it. The tree is just going to be null. And a comparator, which tells us how to organize our values in that tree. What does it mean to come before a node's value or after a node's value? The comparator is going to tell us that. And we want 2 methods that we're going to write in 116 to get our BST working, to get the BST doing what we want it to do, and that's insert and find. So insert, add a node to the BST while maintaining the property of a BST. Everything to the left is less than, everything to the right is greater than, or comparator based, whatever your comparator is. And then find, return a Boolean that just says, is this value in the BST? A little different than our find in linked list where we returned the node containing the value. Here, we're just going to return a Boolean and say, did we find it or did we not? And here's some sample usage. We're going to create a new BST with some comparator. I'm going to use my int increasing comparator, which is the less than operator. So it's going to sort in increasing order. Last time we used the greater than operator and sorted ints in decreasing order. Now we're going to do the default increasing order. So we can just talk about BSTs without getting bogged down with a complex comparator. We're going to call insert a bunch of times to insert these values to create the tree that we've been staring at all lecture. It's going to create that tree with the nodes in the right order. Like 5 was the root. We're going to insert 5 first, then insert the other nodes in a very specific order to get the tree that we want. Then we're going to call find a couple times. This should be true, true, and false. And then we're going to do an in order traversal on the tree. And I'll mention this. I have a slide on this later, but I'll mention it for the first time now. Is an in order traversal on a binary search tree is going to visit the nodes exactly in sorted order. So in order traversal is a very handy traversal to have for BST. It will visit the nodes in fully sorted order. So our in order traversal should visit all of these, and we're printing this out to the screen, should print out all of the nodes in sorted order according to our comparator, which is increasing order for these integers. Okay, so let's go through insert. We have quite a bit of code to look at here. So let's go through this piece by piece. But we have our insert method. Our public method is just inserting a value. We just want the user to give us the value that they're going to insert. That's all we would want to have to provide if we're calling this method. So that's the public facing method. And if the tree is empty, so if the root is null, that means we haven't added anything into this BST yet. So we're going to set the root equal to a new node with that value that's being inserted. Just like we did with the linked list, if the linked list is null, we're representing an empty tree with null. We represent an empty linked list with null. So if we have null in our instance variable, we're going to set the root of the tree to a new node with that first value that's been added, and no child nodes because this is a tree of size 1. If the tree is not null, that means we can actually go through our logic and our algorithm to insert the value. And when I insert, I want to keep track of two things: the value that needs to be inserted, but also the node that we're currently considering for insertion. So again, just like linked lists, when we're setting up our recursion, if we don't have the parameters we need, we're going to write a helper method with the parameters we need. So we know which node we're currently visiting, so we can move through this tree as we try to find a home for this value that we're inserting, and also the value we're inserting itself. So those are the two things I want. I'm going to write a helper method with those two things as parameters, and then call the helper method starting at the root node and forwarding the value that we're inserting. So we're firing off the recursion as a helper method. And then we're going to use our comparator to decide where we're going. What are we doing with this value? And I want to ask one question. Does the value that I'm inserting come before the node's value, the current node that I'm looking at? So I'm pulling out my comparator, calling compare, and say, and our comparator returns a Boolean. It will return true if the first argument comes before the second one and false otherwise, just like our comparators we've been talking about for, I guess, only a week. Or was it only a lecture? It was only a lecture, wasn't it? So not too long, but just the way our comparators have been working since Thursday, since last Thursday. So does this value come before this node's value, which will initially be the root? Because if it comes before it, then we're going to think left. We're thinking left. We got to go over to the left. If it doesn't, we're thinking right. So this code is going to arbitrarily break ties to the right. Doesn't matter which way we break ties as long as we're consistent. And if people are using our code, we should have it well documented too. We should tell people, hey, mainly if ties are allowed or not. So if you're building like a set data structure out of a binary tree, you'd want to not allow ties because a set shouldn't allow duplicate values at all. So it all depends on your application, what you do with the ties. We're just going to break them to the right. All right, so if the value comes before this node's value, we're thinking left. We know this node, this value we're inserting needs to go to the left in this tree. So we're going to look to the left. The first thing we're going to do is check if the left, and we're outside of the binary tree node class, so we have to use our getters and setters. So if we look left and we see null, this node's left value is null, then we found a home for this value we're going to insert. So we can set that left, we can replace this null with a new binary tree node with the value we're inserting and no child nodes, and that's it. The method returns, we hit all the closing braces, that's it. We found a home, we put it there. If left is not null, so we see this node, this value we need to add, and we know it goes to the left of the node that we're currently looking at, but we look over to this node's left child and there's actually something there. There's a node there, so we can't just replace that node. We can't get rid of that node. So we got to do something else. So what we do is recursion. We're just going to recursively call insert helper and move over to that left node and forward the value we're inserting. So we're going to start over the recursion at that next node, and then we're going to do our comparison and do the same thing, just repeat the process. So we're going to move to the left and repeat the process. But we've moved a node. We're using our parameter to traverse, basically traverse. We're not traversing the entire tree, but to navigate this tree to find a home for the value we're inserting. If the comparator returned false, we're thinking right and doing the same thing to the right. So we're going to look right. If we see null, we've found a home for this value. We're going to put it right there and replace that null. If we look to the right and we see a node, so it's right is not null, then we're going to make a recursive call and move over to the right and start the process over again. And that's insert. That's one of our two methods, 50% done with BST methods. Okay, let's see this in action. Say we have this tree right here. We want to insert the value 7. We're going to look at the root node, and remember our comparator is the less than operator here. So we're going to say this value that I'm trying to insert, does it come before this node's value, which for our purpose is 7 less than 5. That's going to say false, so we're going to go into that else block, and we're going to move to the right. We're going to look right. We see a node there, so we're going to make a recursive call on this node and tell this node, hey, we're inserting the value 7. When we get to this node, we're going to ask, does this value we're inserting come before your node's value? So is 7 less than 8? This time it's going to return true. So we're thinking left, and when we look left, we don't see any child node. And I don't have all the nulls here, but if there's no node, you can assume there's null coming off of there. So we look left and it's null. So we found a home for 7 and we insert 7 right there. Then all the recursive calls return. This is a void return method, so they just return, return, return. I want to go through a few more of these. We don't have visuals for more, but I like going through a few more just to make sure we get this. Let's say I want to insert the value 4, or no, let's insert the value 5. Let's do a duplicate just to show what happens. So we'll get here, we'll say is 5 less than 5? That's false. So we'll look right. We don't see null, so we have to move to the right. And then we say is 5 less than 8? True. So we look left, we see a node, so we make a recursive call to this node. Is 5 less than 7? Yes. So we look left, we see null, so we would insert it right here to the left of 7 is where 5 would go. Which can seem a little weird because there's two 5s and they're separated by quite a bit of distance here. But this still maintains the property of a BST. A BST says everything to the left has to be less than, so everything over here needs to be less than 5, and everything to the right needs to be greater than 5, with the option of how we break ties, and we're breaking ties to the right. So in our case, everything to the right needs to be greater than or equal, and that is still true for every single node in the tree. This property needs to be true for every single node. So like at the node 2, everything to the left is less than, everything to the right is greater than or equal. For 5, it's true for the root node. Even if we have 5 to the left of 7, Everything to the right is greater than or equal, and it's still true for 8. Everything to the left is less than, everything to the right is greater than or equal. Same with 7. Everything to the left is less than, and there's nothing to the right. It's true for every single node in the tree that property is. And even with that duplicate 5, it's still true. It doesn't break any of the properties. Even though it looks like, kind of at a glance it would, but it doesn't. So everything's fine. And then say we want to add 3. Let's do one more for good measure. 3 less than 5, true. So we're thinking left. We see a node, so it's a recursive call. 3 less than 2, false. We're thinking right. We see a node, so we make a recursive call. 3 less than 4, true. We're thinking left. We see null, so we insert 3 right here. Gerline, what's up? I'm just having fun talking about trees to basically myself. The 8 a.m. I'm basically just doing for the recording. It's weird, but it is what it is. 11 a.m. gets a little more lively, but not too much. All right, and now let's do the find method. So I'm just sitting in my house talking to my computer for 2.5 hours. It's weird, but since COVID, I've gotten used to it. Find method, we want to do our other method. So that was all insert. I'm removing the insert code just because I can't fit it all on the slide. Let's do the find method. So find, we want to return a Boolean that says, did you find the value or not? And remember, and last time with find, we used the equals method and we said we have a type parameter. We don't know what type this is, but we can use dot equals because everything has dot equals. We're actually going to avoid that this time. And when we get there, I'll talk about it a bit more. But we're actually not using the type parameter at all. So first things first, if root's null, the tree's empty. It doesn't matter what value is, we're returning false. There's nothing in the tree. We're not going to find anything at all, return false. Otherwise, start our recursion, and same thing with insert. We have a helper method that's going to keep track of the node that we're currently visiting to check if it has the value we're looking for and the value we're looking for itself. So we're going to start off at the root and look for this value. And we're going to ask an important question. Does the value we're looking for come before the value at this node? Same question we asked with insert, but a little bit different reasoning. We're going to say, does this value come before this node's value? If it does, then if the value of toFind, if the value we're looking for is in this tree at all, it has to be to the left of this node. That's the only place it can be. It cannot possibly be to the right, or else this is not a binary search tree. If you have this value that's less than this node's value and it's to the right of this node, something went wrong with your BST definition. And with insert, what we're doing is making sure after we insert a value, where we started with a BST, we want to make sure we end with a BST after we insert that value. So the whole algorithm is designed to not break the property of a BST, to maintain that property as we're adding new nodes. With the find algorithm, we're using the other side. We're going to assume we have a BST, and we're going to take advantage of those properties to be able to find this value very quickly. So we're looking to the left. If this value is in the tree at all, it's to the left. If we look to the left and there's nothing, then this value is not in the tree. It has to be to the left, and we look to the left and there's nothing there. Return false. We didn't find what we're looking for. If there is something over there, recursive call to the left. And then we're going to do something we're going to use a little trick here. A nice trick that we can use with comparators is we're going to do the same thing. Because if this returned false, we know that the value that we're looking for either comes to the right of this node's value, is after this node's value, or they're equal. For our less than comparator, toFind, if we ever get to this else, toFind is greater than or equal to this node's value. And if we're trying to find a specific value, we want to know which one is it. Is it greater than or is it equal? We need to know the difference between those. But our comparator doesn't tell us. We can't just ask our comparator, are these two things equal? Because it's saying it's going to return true if the first argument comes before and false otherwise, including ties. So there's two conditions. If it returns false, there's two different situations it can be, and we need to know which one it is. But we can do one little trick. We're going to call the comparator again, but swap the values of the arguments. So now instead of saying, is the value I'm looking for less than, or does the value I'm looking for come before, strictly before this node's value, now we're going to say, does this node's value come strictly before the value that I'm looking for? And if it returns true, if it says, oh yeah, this node's value definitely comes before the value you're looking for. If that returns true, we're thinking right, we're looking right, we're going to the right. Because if this value is in this tree at all, it has to be to the right of this node. So we're going to look right and do the same thing we did with left. If the right is null, it's not in this tree. Otherwise, recursively go over to the right. But the beauty of this is if this comparator returned false both times, there's only one situation left that can be the case. These two values are equal according to the comparator, and we know that we found the value we're looking for, and we can return true. Now notice that this doesn't mean the values are equal. I was very careful to not say that. This doesn't mean the values are equal, but it does mean that their relative order does not matter according to this comparator. For example, if you have a comparator that compares two strings but ignores case, it might have two strings that are not equal to each other, so we can't use dot equals here. They're not equal to each other, but according to that comparator, their relative order doesn't matter. So if we have the same word that's all uppercase and all lowercase, that comparator that ignores case is going to return false and say that those two values are the same, even though they're not literally the same, but they are the same according to that comparator. So, and this is the way that we can get that information, the equals information, out of our comparator. Even though we don't have the comparator flavor that takes that returns an int and does positive, negative, or 0 to give us all three cases, we can make two calls to the comparator with the arguments switched and still get that same information. So our comparator has the same power as the one that returns an int. We just got to do a little extra work and a little extra logic to get that extra information. Okay, so let's find the value 4 in this BST. So the first thing we do, we're going to start at the root, and we're going to say, does the value I'm looking for come before this value at this node? So is 4 less than 5? It's going to return true, so we're thinking left. We look left, we see a node, we don't see null. We see a node, so we're going to make a recursive call over on this node right here. And we're going to ask ourselves, does the value I'm looking for come before this node's value? So is 4 less than 2 for our less than comparator? It's going to return false. So we're not thinking right yet like we did with insert. Instead, we're going to flip the arguments and call our comparator again. Well, if 4 is not less than 2, but it's 2 less than 4, and since we get true here, we're going to move over to the right. Because we know if the value we're looking for is in this tree at all, it has to be to the right. When we get to the right, we're going to do the same thing. We make a recursive call here because we look to the right, we don't see null. We make a recursive call here, and we say, does the value I'm looking for come before the value at this node? So is 4 less than 4? And it says, nah, false. So we know we're not looking left. We know the value we're looking for can't be to the left. But we got to ask another question to see if we're going to the right. So we're going to switch the arguments and say, well, does the value at this node come strictly before the value I'm looking for? So is 4 less than 4? And it's going to say false. No. You just asked me that. No. Still no. So it's going to say no. And since we swapped the arguments and got false both times, there's only one situation left. There's only one thing left that can be the truth. And that's that this node's value, according to the comparator, is the value we're looking for, and we can return true up the recursive calls. Oops. Let's do one more. Let's look for the value 6. So 6 less than 5, false. 5 less than 6, true. We're going to go right. 6 less than 8, true. We're going to go left. 6 less than 7, true. So we're going to go left again. We see null. So we're going to return false, 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 false up the recursion. So if we don't find what we're looking for, we're going to end up at a null eventually, because if 6 is in this tree, it has to be to the left of 7. There's no other place that 6 can go, and there's nothing to the left of 7. Therefore, 6 is not in this tree, and we never had to even look at the left subtree, because 6 cannot be over there, because it has to be to the right of the root. It can't be to the right of 8. It just can't be over there. It's not allowed to be over there if you have a BST, so we don't have to ever check over there, and we end up at our false very quickly. Okay, here's my promised slide on in-order traversal. An in-order traversal on a BST is going to iterate over the nodes in sorted order. This is pretty important to know when you're creating your playlist in task 5. You're going to have a BST, and you're asked to create a playlist of songs that's going to be a linked list of the songs. So you're going to have to accumulate a linked list of songs, very similar to the way we did the string, like the 2-string, the first traversal that we saw. You're going to accumulate, instead of a string, a linked list, so a magnitude or so more complex. But I want to test your retention of linked lists. That's why it's a linked list. So can you manipulate linked lists still? Do you still remember your task 3 stuff while traversing over a tree to be able to get the job done? So you're going to iterate over your BST and accumulate a linked list, and you have to make sure that that playlist of songs is in the order that your comparator specified, which means you want an in-order traversal. If you do an in-order traversal on your BST, you're going in sorted order according to your comparator, whether it's your song title comparator or the Bayesian average comparator. You're getting your nodes, you're visiting your nodes in sorted order. So in-order traversal, by far more useful than the other 2 traversals when you have a BST. Which means, since BST is the only application of binary trees we're seeing in 116, in-order traversal is our go-to. That's our guy. In-order traversal is the one we want. For our code. For your quiz, I can give you any of the 3 for your midterm and final. For the code, you're going to want an in-order. Oh, excuse me. Man, I'm tired today. We're going to do just fine, though. Excuse me. Sorry. All right, BST efficiency. So if a binary tree or binary tree. I'm losing it here. I gotta refocus, lock in here. All right, so a binary tree is balanced if the number of descendants, which would be the size of a subtree, is about the same for the left and right subtrees. To be perfectly balanced, they have to be exactly the same. But as long as they're almost the same, for the purposes of what we're about to talk about, I'm going to call it balanced. So a balanced tree is same number of descendants in left and right subtree. And the tree that we've been seeing today, it's a perfectly balanced tree. And for every single node, the left and right subtrees have the same number of nodes. For the root, left and right both have 3. For each of these nodes, left and right both have 1. And then all the rest of the nodes are what we call leaf nodes, meaning they have no child nodes. So that was a balanced tree. And if you have a balanced BST, then the height of that tree is O of log n. I'm going to throw a little bit of runtime analysis at you. we don't sweat this too much in 116, but I want to talk a little bit about it just so you know why we even bother talking about BSTs. Because why did we even do all this stuff that we just talked about? Is the height of the tree is O of log n, which means it's of an order of magnitude of log n, so it's log n times some constant, basically log n for this purpose. And if the height of your tree is log n, so if you have a balanced binary search tree, your height is log n, and insert and find both take log n time to execute. So both insert and find did a constant amount of work and made one recursive call. So each time it does a constant amount of work, it's going down the tree to go down one child of the tree. And if the height of the tree, which is the path, the longest path from the root to any null, is log n, and you're doing constant amount of work to go down one layer of the tree, then it's going to take you log n time to get to the bottom of the tree for both of these algorithms to run. Which means we do have an effective n log n sorting algorithm. Take your n elements, insert them into the tree. That takes log n per element, so n log n. And then do an in-order traversal. You get an n log n sorting algorithm. You get all your values sorted in n log n time, which is as efficient as we can do comparison sort. Can't do any better than that. Like, provably, we can't do any better. So we have a nice n log n algorithm. In addition to, actually, I think they stopped talking about this in 115, but in addition to merge sort, we stopped talking about it in 116 too, didn't we? We gotta start talking about merge sort again. Is another n log n algorithm. Usually the first one you learn. So big deal. So we can have an array list and call merge sort on it and sort in n log n time anyway. So why do we need another n log n runtime algorithm? What's the advantage? And here finally why we would use a BST is that we can maintain sorted order as the data is changing. So as we have more values we're adding or removing values or updating values, we can maintain sorted order in log n time. We didn't see it, we won't see it in 116, but we can also delete from the tree in log n time. So that means that that we can maintain sorted order on changing data in log n time. We can't do that with arrays, array lists, or linked lists because they'll all take O of n time to update the values. So with an array or an array list, if we have to update the first value in the array at index 0, if we have to add at index 0 especially, we have to move everything down the array list by one value. That's going to take linear or O of n time. With a linked list, it takes O of n time just to find where we're inserting. We have to go .next, 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 and hop all over memory because we don't have random access. We can't just go to the 50th element of a linked list without doing .next 50 times. So both of those are O of n, but a tree can maintain sorted order on changing data very quickly. And I always think of a leaderboard for this. If we have a global leaderboard for a game and we got millions of players and somebody out of nowhere takes that number one spot from everyone else, well, the array list is going to take O of n. If a new player comes along and takes the last spot, the linked list is going to take O of n. You're going to have some bad situations with both of these. A tree says, no big deal, I got you with log n. No matter who it is, no matter what happened, people are moving around the leaderboard and everything. Log n, very efficient to maintain dynamic data in sorted order. That's one of the big advantages of a BST. And one of the big reasons to learn trees at all. Okay, so what is log n? Like, you talk about this in math class, like you're kind of familiar with log n, but I like to put some actual numbers to this and say how efficient log n really is. So log n, and it's a binary tree, everything has 2 nodes, so our base is 2, so log base 2 of n, where n is the number of nodes in the tree. I don't think I defined that earlier. But n, whenever we have runtimes in terms of n is the number of values in your data structure. So what does that actually mean? Well, if we have 7 nodes here, we'll round this up to 8 just because it makes the math easier. Round it up to 8 and say log base 2 of 8. Well, that's going to be 3. And we do see that our height of our tree is 3 from the root to any null is going to take 3 steps. So our height is 3. And when we did our find method or our insert, we're doing 3 recursive calls. Like it all checks out. Like we got our tree of size 7 or 8, and our height was 3. Cool. Okay. That's like half. It's pretty good. A little less than half the nodes we have to visit to be able to get any job done. That's cool. I mean, 50% increase is cool. But how does this scale? What happens when our tree gets bigger? Because if we have honestly, if you have 7 values, who cares what data structure you use? They're all going to take less than a millisecond to do anything, whether it's O of n or log n or anything. So what we're really interested in with data structures and what 250 is going to be all about, CSE 250, is what happens when our data structures are very large. What happens when we have a million elements in these data structures? Because anything less than like 10,000, your choice of data structure doesn't matter all that much, to be honest. But once you get to the really big numbers, once you get to like 100,000, especially a million, then your choice of data structure really matters. You can't be using the inefficient data structures at that point. Or you can't be using the wrong data structure for the job. So what happens when our BST gets a million nodes in it? What's going to be the height of that tree? So what's log base 2 of a million? Because with 7, it was about half. What about a million? How does this scale? What is log n? So with a million nodes, the height of that tree is going to be 20. It's actually a little less than 20. 20 nodes. So if we have a million nodes in our BST and we want to find a specific value, we only have to look at 20 of those nodes. Log base n, or log of n, is almost free. Like it's such an efficient algorithm. If you have a log n runtime, it's basically free. I mean, a million nodes, you have to check 20, and this keeps scaling incredibly well. If we have a billion nodes, it's 30. Every time you add 3 zeros here, you're only adding 10 here. So a trillion, you're checking 40 nodes. Like we can check 40 nodes. That's easy. We could do that by hand. If you had a tree with a trillion nodes in it, and I ask you, and it's a BST, it's all perfectly balanced and everything, and I ask you, does this tree have this specific value? Does this tree have the value 640 in it? You could do that by hand. You can check 40 nodes, go through the tree, looking for that value, and it wouldn't take you very long. For a computer, it's basically instant. It's instantaneous. So log base n algorithms, these are extremely efficient. We like our log base n algorithms. They're nice. This is also how you get your 20 questions games. If you ever played the 20 questions, you have the thing that asks you a bunch of yes or no questions. It's a little trickier than that, but it's basically a binary search tree where it starts at the root, asks you a question, and goes left or right based on your answer. And it's basically doing a search through a binary search tree. The reason it's a little more complicated is often we as humans will answer some of those questions incorrectly. So it has to have a little extra logic to be able to handle our incorrect answers. So it can't strictly just be a BST, or else it would get, once we have one wrong answer, it'll get completely lost in the tree. But this is the same math, the same reasoning, why the 20 questions game does work, why it can have a million different solutions and only ask you 20 yes or no questions and get to one very, very specific thing that you were thinking of. It's all the power of math. Math is nice. Math is our friend. But all of that is if the tree is balanced. That's a big if. And we don't satisfy that if in 116. We didn't even come close. Because I was very careful. I manipulated quite a bit to make sure that everything was going to be balanced. But what happens if we create a BST and insert our values in sorted order? So we call insert with -3. That's going to be the root. The tree is null. we insert 2. We say, does the value we're inserting come before this node's value? False. So we go right. We see null. We insert. 4, go right, and insert. 5, go right, insert. Same thing, 7, 8, 14. We're just going to keep going right because that's what our algorithm says. This value doesn't come before the node's value, so we're going to go to the right. And now we basically have a linked list, which has horrible efficiency. Everything's going to be O of n, insert and find. Our height is O of n, insert and find are both O of n, and we lose all of our efficiency. We might as well just use the linked list from the beginning, because that's basically what we have here. We have no efficiency at all. So we'd lose any gains that we might have gotten by using a BST. Excuse me, which is bad. So to take care of this, we need to be able to handle these situations where a tree gets unbalanced and still insert, find, and delete, which we don't even attempt in 116. We want to do all 3 of those operations in log n time. How do we do that? While maintaining the property of a BST and maintain sorted order, but that's the property of a BST. How do we maintain the property of a BST while doing these things in log n time and keeping the tree balanced? These are some great questions that'll be answered in CSE 250 when you talk about AVL trees and red-black trees. Those are the ones you'll learn there. And the short answer, for those of you interested, is when you insert 4, I think both AVL and red-black, probably when you insert 4 would trigger their logic. It would be a rotation. So in general, once it detects that the tree is getting imbalanced, you'll have a rotation, which is going to shift these nodes around. So once you insert 4, it says, whoa, we're getting imbalanced. Let's fix this. And it'll rotate these 3 nodes to push 2 to be the new root. -3 will be the left child of 2, and 4 will be the right child of 2. And as we add more of these nodes, it'll get imbalanced again, and it'll have more rotations to fix up the tree. And it might have multiple rotations by the time you get to the end. We might have a new root. The root might be 4 instead of 2, might even be all the way to 5, and create that balanced tree that we had on the previous slides. So that'll all be answered in 250, and you'll actually get the efficiency from a BST. So we don't get the efficiency in 116. The way we wrote our algorithms are very basic, very kind of potentially inefficient for these reasons. But you will learn about self-balancing binary search trees in CSE 250. So you will actually get the full gains in 250. Okay. And we're ready for some live coding. And I'm going to do tree sum. What's example? Oh, I think somebody asked the question, and I'm not sure why I did that one once. But I'll talk about it since I opened it. If I want a binary search tree of, say, health potions of whatever type, I'll create a comparator for health potions. So I have my comparator, which I'm going to sort in decreasing order based on the amount of health that they restore. Add them all to my BST with different increased values, and they'll be printed in sorted order. So I got the health potion healing 100, then 50, then 10, then 7. So they're all in decreasing order according to their increased value. So whatever comparator I want to give it, and then create my tree with that comparator, it will sort in that order. Tree sum, that's the one I want to do here. So let's create a class. Let me just double check. Not creative, so I'm just going to call it tree sum again, except maybe spell it correctly. doing on time? Oh, we got tons of time. All right. Tree sum tests. How did I do that twice? And we need thingy. We need some class. I just need a class that's going to have some instance variables so we have something to work with. I want to give an example of working with a binary tree of some object type because that's what you're asked to do on the homework. You're going to have a binary tree of song objects. So I need some object. I'm just going to call it thingy. I don't know. I need something. I always come up with, I think it's thingamabob in the repo. But I just need something that has some instance variables to be able to work with. And I think I only do one instance variable. Let me be consistent, just in a string. Yeah, I'll do two. So a string description, sure, and private. I don't want to say value because I'm just overusing that that thing. Let's do magnitude as an int. All right, so this is my thing. I need a constructor, public thingy string description int magnitude this dot magnitude equals magnitude. I like to have them in order. This dot description equals description. I don't really need setters, but I do want my getters. Public int get magnitude. I'll take the autocomplete there. That is literally what I was going to type, so that's fine. Return this dot magnitude. Public string. Actually, I'll probably never call this getter, but let's get it in there anyway. Return this description. And I want a method that's going to go through a tree of thingies. I kind of wish I named it something else. I'll have to think of something better for the next lecture. Goes through a tree of thingies and returns the sum of all the magnitudes of the values in that tree. So I want to write a method, and it's going to be a static method because I don't need any instance variables in tree. Oh, no, it's not. What am I doing? Oh. So I want a method that's going to return an int and sum of magnitudes. Sounds fine. And for now, I'm just going to return 0. I'm going to have a method public void, a way to add a thingy. Which I'm not going to implement yet. And I need a constructor here. Public tree sum. Actually, do I even need a constructor? I can use the default constructor here. So these are the two methods I'll need, and I'm ready to write some tests for this. So let's see if I can get the auto import to get my test annotation. Looks like I can. Public void test tree sum, and I want to create a new tree sum tree. I'll call it tree. New tree sum tree dot add thingy new thingy of first thing, whatever, 5. We'll call this one Chad. Yo, yo, yo. Has a 17. Oh, I'm going to make the math hard on myself, ain't I? Ellipses. Make the math a little easier on me on that one. Great. And this can be 10 to make the math easier on me again. And then tree, my expected int tree equals, expected equals tree dot sum of magnitudes. What am I doing? My actual and my expected is actually a good reason to make this point is whenever you have a test case, whenever I'm writing a test case, I like to use some outside resource to be able to get my expected values. Often that's a calculator, sometimes it's a spreadsheet, but I'll use something other than my code to generate the expected values, especially when the math, when the expected value, I just can't compute it in my head. Yeah, I could do this one, but I'm just inviting human error at that point. I might be off by 1 on my solution, and if my test case is broken, I'm going to think my code's broken. Then eventually I have to look at my test case to see if, I don't know, I'll just use the calculator. 5 plus 9 plus 17 plus 1 plus 10. But the 40A, nice sum. But the important thing there is don't use your code to generate your test cases. Way too many, not just students, but developers fall into this trap of using their code to generate their test cases. If you use your code to generate your test cases, your code's going to pass. Like you're going to pass those tests because it's your code being used to test your code. If your code's wrong, it's going to generate wrong test cases, but your code's going to pass those wrong test cases. And now you have bugs without knowing you have bugs because of the way you generated your tests. And we don't like that. That's not how we do it. It's just not what we do. I'm only going to write one test case here. Obviously, if this were, I would write more test cases, but in the interest of time, actually, we're going to do fine on time anyway. So let's run this. It passes. See, oh yay, another good thing I get to talk about. So this passes because I forgot my assert. So I'm expecting that to fail. I always run my test cases. I want to see them fail to make sure they're actually testing something. This one passed, which means I know it's not testing anything. And obviously, I just didn't finish writing the test. Hey, it happens sometimes. That's what I'm talking about. Human error happens. We do it all the time. We all do it. Writing your code in a way that's going to limit the amount of damage that human error can do, like having our override annotations, watching our test cases fail, using the calculator to generate our expected values, a lot of things like that to limit the amount of damage my human brain can do. Assert equals. It is going to make me do my import, so import static org.junit dot assert, the assert class, and I'm going to import all of my asserts from that class. So now I have assert equals and expected actual. Sometimes I like typing them out just to emphasize the point that autocomplete types exactly what I was going to type. So every once in a while I'll type a line like that just to emphasize my point that, hey, autocomplete, I'm literally just saving keystrokes, nothing else. It's not doing any of the work or thinking for me. Very important that you do the same in your assignments. If I call you in for a meeting and say, can you explain your code and your thought process here, and you go, oh, gee golly, I don't know, I'm just going to assume that you didn't write the code, and it's an AIF. It's an AI violation. Be mindful of that. Don't have something else write your code for you. As tempting as it may be, don't do it. Even if I don't catch you and you don't have that meeting, you're gonna fail eventually in another class. Like if you don't know what you're doing, I'm seeing way too many students fall into that trap these days. They have no idea what they're doing because they use outside resources, mainly AI. It's a problem. It's a problem I'm trying to fight, but really it's a problem for the students who are doing it because they graduate and don't know a damn thing. Then they say, "Oh, gee, the job market's so bad." Well, it's not great right now, but if you don't know anything, no one's going to hire you. It's as simple as that. So we're going to need a binary search tree. I don't know. Hopefully none of you need to hear that right now, but if you do, let that hopefully you heed that advice, because I don't like seeing students like, my job is to get you a job. I don't like to see students not getting jobs. So we're going to create a binary tree of thingies. That's going to be our root. I'll just set it equal to null right here. And I did this exactly wrong. This is exactly what I tell students not to do. So I can do this. I can create a binary tree node and create my tree manually, do all my binary tree stuff. No, we're not even doing, no, never mind. We're not even doing, do I want to do that? Wait, I have to cheat a little bit, sorry. Yeah. So I set this up different than I meant to. But that's cool because I just show you different stuff. So I'm going to create this as a BST, mostly just because, well, this will actually match closer to what you're doing on your homework anyway. But because I have an insert method. So in the other example, what I was cheating there, I would create the binary trees manually in the test cases. So I'm manually creating my trees, and then tree sum was a static method that just took a tree, and returned the sum of all the values. So here I set this up a little different. I have an add method, and this is a little closer to what you're going to see in the homework anyway. And then I'm using the add method to create the tree. So I'm going to use the BST so I don't have to write an add method mostly. I don't want to have to write an add method for a regular binary tree. So I'm going to do BST. And when I create a BST, I'm going to need a comparator too. I'm going to need a new BST. So I'm not setting this equal to null, because in the BST class, root is going to be null. So my tree is still empty. It's still a variable assigned the value of null, but I don't have to mess with that in my code if I'm creating a BST. What I do need is a comparator of thingies. So let's do a thingy comparator. Thingy comparator, which extends comparator of thingy. I got week 7 lecture comparator BST. Let me just make sure my imports match. Week 7 comparator. Week 7 lecture comparator. I want week 7 comparator. Make sure I import the right comparator. Then I want to use my override annotation to make sure I am actually overriding something, because I might not remember exactly how this was set up. It was a Boolean. I think I do remember, but there's a Boolean called compare that's going to take two thingies. Thing 1, thing 2, I'll call them. And then I need some way to compare them. For this use case, I'm actually not using the property of a BST. I'm just using the BST for its insert method, so I can do this dot root dot insert. So I can take advantage of that insert method that we already wrote. So I don't actually care what's being compared. I just got to have some comparator here. So let's do return thing1 dot get description. And hey, I actually am using that getter that I said I wasn't going to use. I'm going to use compare to ignore case thing2. So let's sort by in alphabetical order based on description. Get description, and if compared to ignore case returns a negative value, meaning the calling object comes first, then I want to return true. So I want to return if this is less than 0. So if this is less than 0, so if this is negative, I'll get true and false otherwise. There's spoilers there, but most of you are past task 4 anyway. New thingy comparator, because the BST needs a comparator to know how to sort things, how to organize things. And then we get our sum of magnitudes. Now we can do our accumulator pattern for sum of magnitudes. So I want to say if, and it's not really accurate to call this root anymore. This is not a reference to the root of a binary search tree. This itself is a BST. So if this dot BST dot get root, if the root of the tree, if the tree is empty, I'm just going to return 0. The sum of magnitudes, there's just nothing there, nothing to do. Else, I want to set up my recursion. So I'm going to set up a helper method which has all of the parameters that I need. Just some helper. I'm just going to return an int. And what I need here is the node I'm visiting. That's definitely going to be a necessity. The node of thingy that I'm currently visiting. And I could set my accumulator. There's a question of what to do with the accumulator. I can have it here, but I feel like I've done that enough times. I kind of want to show you something else. So I'm going to accumulate in the method itself. And then I'm going to return some helper of this dot bst dot get root. So I'm going to start at the root and go through my accumulator through my recursion. So inside the recursion, I'm going to check if, actually I'll do it this other way. So int sum equals 0. Actually, I don't have to do that. If int sum can be node dot get value. Now the value of the node is a reference to a thingy object on the heap. So get value is a thingy, and then I need to get its magnitude by calling its getter. So we'll set sum equal to that, and then we're going to say if node dot get left is not equal to null. So we're going to do the other flavor here. So if left is not null, then we can make a recursive call to the left and accumulate that into our accumulator. So sum helper node dot get left, and also if node dot get right is not null, we're going to make a separate recursive call to the right and accumulate that into our sum variable. Sum helper node dot get right and return sum. If you embrace recursion, these tree methods are pretty easy to write. I effectively did a pre-order traversal here, but addition is commutative, so it really doesn't matter what order we visit things in. Let's run our test, see how we did. Green's always good. We passed our test. And if we look at this, let's crack open the debugger. Let me explain that code a little more. So we're setting sum equal to the value at the node that we know we need to process this node, and we're conditionally making our calls to the left and right. So we're checking, is the left null? If it's not null, make a recursive call to the left, and whatever it returns, add that into our variable. And let's look to the right. If right isn't null, make the recursive call to the right and add that to our variable as well. And then this should be the sum of the left subtree, the right subtree, and this node's value. Now I don't have to check if node is null because I'm never making a recursive call where node is null. In the previous example, I checked if node not equal to null, then do the stuff. Here, I'm never making a call where node's not null. If left is null, I don't make a recursive call. If right's null, I don't make the recursive call. And if the root's null, I don't make the first recursive call. So node is never going to be null because I'm making my null checks before I make the recursive calls. Where before, I just always unconditionally made the recursive calls, and then if node was null, if I happen to call the method on null, then I would handle it there and not do anything. This is very similar to the structure that you'll do in task 5, except instead of accumulating an int, you'll be accumulating a linked list. So it'll have a bit more complexity there. You have to remember all of our linked list discussion. You'll make your left recursive call, that's going to return a linked list. Your right recursive call, which will return a linked list. And then you want to create a linked list for the node that you're visiting. And then your task, the bulk of the difficulty is combining these 3 linked lists, which admittedly isn't too difficult, but it's in the context of your first recursion with trees. So it gets a little tricky. Depending on how well you know your linked lists is really what it depends on. And that's kind of my goal, is to make sure you understand your linked lists, your node-based data structures, your trees. If you know all that stuff, it's not too bad. Okay, so now let's crack open the debugger. And we should see all of these values in the tree sorted in, well, after they're all inserted, we should see them all sorted in alphabetical order. And I have the capital C here, but that's not going to matter because I did compare to ignore case. So we shouldn't get that C really affecting anything. It should be in alphabetical order. And now I regret doing the ellipses. I think this should be first, but let's just see. So the tree has a BST. Its root has the value first thing, because that's the first thing added. And then everything to the left needs to come alphabetically before first thing. So C comes before F. To the left, we have ellipses comes before F. So C and F are things that are coming, or C and ellipses coming before F. That checks out. And then Y and G both come after F. So they should both be on the other side. So left, and then ellipses was to the left of Chad. The period comes before C in alphabetical order. So to the right of the root, we have the value yo. So Y, and then to the left of that, so this should come before Y, which is G. That looks, all checks out. So G coming before Y. Looks like our binary tree is sorting in the order of that comparator, which is exactly what we wanted. And then our recursion, our root's not null. So we're going to go through the helper method. For the root, the magnitude is 5, so sum is going to be 5. So sum is now 5. And then the left is not null. it's a node with the value with this value and everything. It's not null, so we're going to make a recursive call on its left node. We're going to put another frame on the stack where node, I was looking at the wrong spot, where node is that left node. So now node is a reference to this node with the value Chad. Its left has the value ellipses with 1. So this is going to get Chad's value 9. So sum is now 9. We're going to look to the left. We're going to see a node, so we're going to make that recursive call. And in this recursive call, so we have another frame on the stack. In this recursive call, the node is this node with the ellipses and magnitude of 1. So magnitude is going to be 1 right here, or sum is going to be 1 right here. We're going to look to the left and see null, so we will not make this recursive call. We're going to look to the right. We're going to see null, so we're not going to make that recursive call. We're just going to return 1. So that stack frame ended. We're back to this stack frame, which just made its left recursive call. Sum was 9. That was the value of this node. And sum helper just returned 1. So now sum is going to be 10. So we added that 1 to it. We're going to look to the right and see null. So we do not make that recursive call. And we return 10 back to the first stack frame. So sum was 5. That's the value of this node. It's getting the return value of 10, so sum is going to be 15. After we do that addition, we're going to look to the right, and we see a node. We see a bunch of stuff over there. So we are going to make the right recursive call. And now node is this node. The value of sum is going to be 17, the value of this node's magnitude. We're going to look to the left. We do see a node here. So we're going to make this recursive call. Oops. I want to go into the getters. The magnitude is 10, so sum gets the value 10. We're going to look left, see nothing, no recursive call. Look right, see nothing, no recursive call. Return 10. That gets back to this stack frame, which has the value 17. We're going to add 10 to that up to 27. We're going to look right and see nothing, so no recursive call. Return 27 back to the first stack frame, which was waiting for its right recursive call to end. We're going to add 27 and 15 to get our final 42, and then return 42. So we return that back to the original caller. Actual, let's collapse all this. Actual is 42. Expected is 42. Those equal each other. Test case passes. All right. Does anybody have questions? I feel like I'm not going to get questions in this, but does anyone have questions? Because, I mean, kind of ran out of, like, that's the stuff that I wanted to say. If anyone has questions, I'll be happy to take them. We do have a little time here. If not, I'm just going to shut down the stream. Because we got through everything. We did introduce binary tree nodes, BSTs, did some live coding. Got an example that mirrors a bit closely to the way your homework is going to behave. We're accumulating an int instead of a linked list. That's the big difference here. But this is the structure that we want to follow for your task 5. You're going to create this playlist class that compares songs. It's going to take a comparator of songs, and then you want to create a BST inside the playlist class. You're going to have a BST, just like we did in the example we just saw. Create a playlist, not a playlist class, a playlist. In the playlist class, you'll create a BST object as an instance variable would be the way to approach this one. Add song, get song tree, a couple getters. This is mostly for testing purposes, makes testing a little easier for you and us. And get song list, this is the big one that you'll be working on. Get song list is going to return a linked list of all the songs in sorted order according to the comparator, which is your in-order traversal, and you're accumulating all those songs into a linked list. That's the bulk of the assignment here. And your testing utility is comparing two trees for equality, which, again, I always recommend using the utility method in your test. You're not going to get null pointer exceptions if you use that utility method. And then your tests themselves. Create your trees. If you manually create your trees that you expect and then call your get song list method, you can do that comparison using your utility method. That's test 5. I don't see any questions in chat, so I'm just going to end it here. I got through everything I wanted to talk about. You have everything you need for trees. Good luck on the midterm exam. Make sure you're getting ready for that. And I'll see you after the midterm for file I/O. All right, take care, everybody.